Okay, so it's a pleasure to introduce Alberto Pinto from the University of Porto. He's going to talk about one-dimensional chaotic attractors.
Thank you. Thank you. So, a long time ago, I was a PhD student at Warwick, and with David Rand, my former supervisor, I went to IHS. We went to IHS together to visit Dennis Sullivan. And when I was visiting IHS, I had the pleasure to meet Maurício Peixoto. And we started talking. We ended up to be very good friends. And through Maurício Peixoto, I met later Welington de Melo in Portugal. He came to visit Portugal for a short period, and we started our first work there. After that, I started visiting IMPA, and now I'm doing it for more than 20 years. So I learned a lot with both, and also both like family for me. So thank you very much for all the encouragement and help through all those years. Okay, so I'm going to talk about one-dimensional chaotic attractors. I will not cite many people because a lot of contributors are here, so I don't have really to say their names. But of course, Sullivan is one of those names, and I got into this subject exactly in that my first visit to IHS, where I heard Dennis Sullivan talking about this at that time. So I'll start for a short motivation, and that it is. So as everyone knows, Lebesgue proved that the homeomorphism from the interval has derivative. So the problem is that this derivative might be zero. So, okay, it has derivative almost everywhere, but is it zero or it's not zero? So for quadratic like unimodal maps with negative shores and if we assume that they are topological conjugated by H, and if F has a positive Lyapunov exponent, Lebesgue almost everywhere, we are able to prove a dichotomic result. So either H is a CR diffeomorphism or has derivative almost everywhere. So what I'm presenting is a work that we are doing at the moment, that I'm doing with Wilton Pinheiro from Bahia, Salvador. So this is a natural extension. So here we use a result of Lubitsch, in fact, to get our result. So this result is a natural extension. So if you use Keller, we know that for interval map, and now with negative Schwarz and positive Lyapunov exponent, we have a finite collection of attractors. And so we can apply again our result to prove that for each attractor, either the conjugacy has derivative zero in a set with full Lebesgue measure, or it is a CR diffeomorphism. So again, we get this dichotomy that I have shown to you before. So our aim was not only to prove these results, but to extend the theory for the case where the map F has a discontinuity set. So we can extend these results, and that's our main contribution for the case where F now is only a CR piecewise interval map with a non-flat discontinuity set. So in this non-discontinuity set, we can have critical points or singular points. It doesn't have to be critical. It can be singular as well. So as a first step of our proof, we extend to this set a previous result. So for cycle interval maps, we show that a chaotic topological attractor, and I'll say later what it is, and it's like the first definition I heard, or related with it. If and only if there is a measure mu that has a Lyapunov exponent, slow recurrence, and full support in the chaotic topological attractor. We show that it's equivalent. So a topological argument is equivalent to a metric argument. So I'll start by explaining a little bit this result, or the steps that drove us to it, and then I will just use it to prove the explosion of smoothness. So my talk is orthogonal, like I was thinking about this yesterday, to Edson talk. In Edson talk, it doesn't have periodic orbits. In my talk, I need to have one periodic orbit. That's the point. So the point of my talk is I need to have one, and with one periodic orbit, I'm fine. And Edson could not have any periodic orbit. And with one, I will have a lot of periodic orbits. So that's what I'm going to talk about. So by a piecewise CR map with a non-flat discontinuity set, I mean the usual definition. So I don't need to go through it. And here, we made the option not to have the map defined on the critical set. If I have it defined or not, it doesn't matter. But like for what we want to do, that is this explosion of smoothness, it's easier to write results if I consider that the map on the critical set. I don't use the map on the critical set. So I consider that F is in I minus the critical set. So when I will use the notion of orbits, you know that I don't iterate through the critical set. I'm not iterating either forward or backward through the critical set. This is not relevant, but makes notation easier. So bias cycle intervals, I will not give the standard definition, but very close to the standard definition, and standard definition is included in ours. So somehow the standard definition of cycle interval is minimal in our sense, and we'd like to extend it to an added notion that it's like maximal, to a maximal cycle of intervals. The difference between the minimal and maximal cycle of intervals is a finite set of points. So again, it really doesn't matter, but makes the results much more neat if I use this construction. So the difference between the usual and our definition is that here I say the interiors of the intervals are pairwise disjoint. Usually we don't put the word interiors in this definition. When I do that, as I explained, I will get rid of a finite set of points. That's the only difference. In bias cycle of intervals, we mean as usual that we have a finite set of intervals and the map permutes this set of intervals. So given a cycle of intervals, we can try to find a maximal one. So it will have the same support of the previous one, but we'll try to find one cycle of intervals that has the higher number of intervals that are permutated. And as I have said, in our case, the difference between, first we prove that it exists, this maximal cycle, and then we show that difference between two is only a finite number of points. And the reason that I want to get rid of this finite set of points is for the results in explosion of smoothness. It's not for this first part of the talk. So as usual, we say that a pair FA induces a topological horseshoe if we can find open intervals, return times, to construct our horseshoe. In this construction, I'm just talking about topological horseshoe, so I'm not assuming any expanding properties, it's like smooth properties of these maps. So it's a topological definition. Of course, the map is smooth because that F is smooth, but I'm not requiring any expanding expansion of this topological horseshoe. So with that, I present the definition of a chaotic topological attractor. So F is a piecewise CR interval map. A is a cycle of intervals, and we ask that this cycle of intervals induces a topological horseshoe. In that case, that's like the definition that we take here for a chaotic topological attractor, which is sort of standard, if there is a standard definition, which there is not. But okay. So from this definition, we know that if F is in fact a CR interval map and not only a piecewise interval map, then this support of A is already a chaotic topological attractor. The problem is that since we have discontinuities, there are well-known counterexamples, like the irrational rotations of the circle or the Sherry attractors that come from like the Lorentz attractor. So to have a cycle of attractors is not enough in our setup to have immediately the chaotic topological attractor. We have to say something more. So from this topological perspective, here we move to what we are calling the Markov map, which is an horseshoe, but with some nice smooth properties. So when I talk about Markov map, I have C1 plus alpha diffeomorphisms, and as usual, we have bounded distortion. So these already have all the nice analytic properties that we like to have. And for Markov map here, we also consider that the components are an open dense set of B. So, yes, uniformly. This is really the usual nice maps that I like from a long time ago, with an infinite set of components. Okay. So now going to the part where my talk is different from the talk of Edson. So I need to have a periodic point. And this periodic point, the only property that I ask is that its alpha limit is not finite. So we call this entropy generator. So the entropy generator set is the set of all these periodic points that have the alpha limit is not finite. And for these points, I'm not asking that they are expanding in the sense that they have a positively Lyapunov exponent. So for this set of periodic points, I'm not asking that they have a positively Lyapunov exponent. And when I drop this 0, so epsilon A for these points here, I'm already asking that they have a positively Lyapunov exponent. So this again is sort of a topological setup, and here that's where I get the analysis, where I get the expansion. And so that's our first result. So for these piecewise CR interval maps and A cycle intervals, AM will be the corresponding maximal cycle of intervals that we prove that it exists. So it's not taken a priori. In fact, it's part of the proof. We show the following. We show that FA is in fact a chaotic topological attractor if we have one of those periodic points. So if we have at least one periodic point whose alpha limit is non-trivial, then that's enough. So that's like the setup is now totally different from the setup of Edson. I like to make this difference because I love to work with Edson, and we have at least one paper together. So that's okay. So now, so to know that we have a chaotic topological attractor is enough then to have this one periodic orbit with a non-trivial alpha limit set. And now if we have this chaotic topological attractor, it has several nice properties that usually these chaotic topological attractors have. So now I drop this 0, I have this epsilon A, so now all these periodic orbits are expanding. They will form a dense set in support of A, which is equal to the support of the maximal cycle of intervals. These two sets are the same. And now this set is set of all expanding periodic points in the interior of our AM. So that's the reason I want to lose this finite set of points, because then this is the full set of expanding periodic orbits. For every periodic point in this set, we also have a Markov map such that this point is contained in the periodic points of the Markov map. So here I got all the expansion that I need. So starting with this topological, this periodic point, we are able to get the Markov maps. And here for points that are dense in the attractor. The maximal, so this maximal cycle of intervals also has this nice property. So if we start with a Markov map, if we iterate the set forward, we get the full maximal attractor, the maximal cycle. So after we got this result, we could keep going. And so now discussing the measures, so the ergodic measures, as everyone knows here. So an ergodic inversion measure has a positive Lyapunov exponent if it expands almost everywhere with respect to the basin of that measure. It has slow recurrence if it doesn't get too close of the critical set. And so we define a fat expanding measure as being an ergodic invariant measure with a positive Lyapunov exponent, with slow recurrence, so the usual ingredients, and the interior of support being different from 0. So if we have one of these fat expanding measures, we get that A is a topological chaotic attractor, and we also have the converse result. So if F is a CR-piecewise interval map, we don't have control in this discontinuity set. It can be critical or singular. A cycle of intervals is a chaotic topological attractor if and only if such measure exists, such fat expanding measure exists, and support is the cycle of intervals. So that's our setup for CR-piecewise interval maps. After we have this setup, then we pass to the second step to get the explosion of smoothness in this setup. So two chaotic topological attractors are topologically conjugate if there is a conjugacy that conjugates them in the proper way. And if we have such a topological conjugacy, we say that the Markov map for F synchronizes with G if when we push it forward to G, it generates also a Markov map. So of course, not all Markov maps need to synchronize, or not even one Markov map. So when we have a Markov map, we just look to the ones that synchronize, that their image is also a Markov map for G. So that's what I mean by synchronization. Yes. The measure is not absolutely continuous with respect to back. Not at all. Thank you. Sorry. Thank you. I should have said it. Thank you. Definitely. Definitely. Thank you. It has a nice support anyway. So that's the only thing we say, is that the measure has a nice support. The support is the cycle of intervals. Okay. So a Markov map synchronizes if its image is also a Markov map. And so when I put this H, I'm talking about the Markov maps that synchronize. When I don't have this H, I'm not saying that they synchronize. So for a Markov map, we define our set of interest is nu of f, and the property that we need these points to have is that their omega limit contains an interval. So now, given one Markov map, I look to the points whose orbit is dense. So whose orbit is V. What I need, in fact, is that they contain an interval. If they contain an interval, they contain V. So from this set, we construct the visiting set for the tractor as the union over all Markov maps. And the synchronized visiting set can be smaller than that one, because now I take the union of all these sets, but only for Markov maps that synchronize. When I have the H, they have to synchronize. When I don't have the H, I don't care if they synchronize or not. And so I can pass to the results. So the first result that we have is that this synchronized visiting set is not too small. So from a topological point of view, it's a nice set. It's a residual set. And so that gives us the theorem. So the theorem says that if H is differentiable, and here by differentiable is the usual notion of differentiability. We are not using C1, just differentiability. Because it refers to the Markov maps of F that are also very nice Markov maps for G, in the sense that they are also nicely expanding there. So that's when they are synchronized, F and G, in this expanding part of the maps. So this set is residual, so from a topological point of view, it's fine. And now we only need to have differentiability at a point, the usual differentiability, no C1 here. And with that, we get that the conjugacy is in fact smooth. And we get it smooth in these maximal cycles. That's the reason I wanted to lose that finite set of orbits, because they were there only to bother us. So now I have a similar result, but instead of talking about the synchronized set, now I'm talking the set that doesn't have to be synchronized. So this is much larger, or can be much larger than the previous one. But to gain here more points, I have to lose something. So when I take this set as non-being synchronized one, I have to get some control of my second map, of map G. So the usual control, so negative Schwarzschild, or something like that is like negative Schwarzschild. I have to put a negative Schwarzschild somehow in the second map. So I get a bigger set of points, but I lose in my map G. That's the price that we have to pay. And so from this I get to my last slide. So why did we want to get the result for this bigger set, the visiting set that doesn't have to be synchronized? Because now this set has full back measure if the measure behaves as Lubitsch asked. So if you have a measure that is absolutely continuous, then this set, the one that doesn't synchronize, has full back measure. And with this result, we can use Keller's theorem or the extension of Kelly's theorem for these maps with discontinuities and prove the result that I showed as a motivation for the talk. And that's it.
Okay, so are there any questions, comments?